Oops. Thank you. Very good. Can you hear me? Yeah, I suppose so. Well, okay, let's see. Thank you very much for being here. So the talk today, I'm going to try to do it like this. So the talk today is actually, this title is a little pretentious, but I didn't know what I was going to say. So I just put so the real title of this talk is this. This is about nonlinear optics, and it's about the use of intense light pulses to drive cooperative phenomena, meaning collective excitations in solids, which means that I will be studying the use of these light pulses to control these phenomena, especially in complex solids. And by complex solids, I mean complex materials, or what we usually refer to as correlated electron systems, which exhibit very interesting properties in equilibrium and under stimulation. So, so this talk starts as a talk about nonlinear optics. So I will sort of introduce a few basic concepts of nonlinear optics at far, or what's new about, or new things that can be seen in nonlinear optics at long wavelengths. Then I'll give you a few examples, and I will, most of the talk, I will make one example that is probably palatable for most people that don't work in our field, and then I will take the privilege of basically stealing 15 minutes to give you a bit more of a technical short talk about some physics in the cuprates that we're quite excited about. So there's going to be a little bit for everybody. So let's see. So this is, optical spectroscopy, linear optical spectroscopy has been used for a long time to look at excitations in solids. As long as some collective excitation is dipolar, has a dipole, and is at long enough wavelengths to be observable with light, one can probe it. And a lot of work, of course, is done in the visible. Generally, the visible excitations have to do with, say, interband transitions in solids, in semiconductors, but also more sort of complex materials. And as I go further away in the mid-infrared, I see collective mode responses. So I've sort of, in a broad brush way, I've highlighted here the region between, say, 200 millieV energy and maybe a few millieV, which is where phonon resonances are. This, I'll be discussing a lot about this. And then even at longer wavelengths, there's signatures of collective modes, and I will be discussing this. So anyway, optical spectroscopy, linear optical spectroscopy has been incredibly insightful probe. If you look at an optical spectrum over a few decades of frequency, there's an enormous amount of information. There are some rules there. There's lots of things that you can learn. It's, as people develop lasers, there's been now, we're almost 60 years since, I think it's almost exactly 60 years next year, since the development of nonlinear optics. As soon as light pulses could be made strong enough, then completely new horizons in spectroscopy emerged. So basically, nonlinear optics is about shining a light field at one wavelength, say, onto a material and looking at light coming off at different wavelengths. And it's very interesting because, very useful because there's new selection rules compared to what one finds in linear response. So for example, I can look at two photon transitions between orbitals of similar symmetry. You can look at surfaces. I can rotate polarizations in various ways and learn about symmetries, et cetera, et cetera. But by and large, most of the work, so this is one of many famous books, at least that's one of the ones that I've learned nonlinear optics on. Most of the work to date has been done in the visible. And the reason for this is that it's, lasers are developed in the visible naturally. They will work between regions around 1 eV and 2 or 3 eV, say. And so naturally, a lot of work has been done there. But there's a lot of things to be done if one can start looking at the nonlinear response of this region of the spectrum. Okay, so let's say between, as I said, 100 millieV down. And there's two things that one can do. One, again, like in nonlinear optics, one can use these nonlinear responses as a spectroscopic tool. But also one can use, rather than using a material to manipulate the light and to change the properties of the light, one can use the light to change the material. Of course, this is done in the visible, but At some level, because dissipation is lower at this lower frequencies, and because one can be selective in new ways, there's new means to manipulate materials. So this is what this talk will have, a little bit of one and a little bit of two. So specifically, there's many excitations that one can study, and we've been doing some work in many fields, but the discussion today is going to be about nonlinear response of phonons. So I'll you know, sort of tongue-in-cheek, I'll tell you about nonlinear phononics. So let's say that I have a certain material that has a number of optical phonons, and they are optical because they appear in the optical spectra. And I'm interested in the phonons that are symmetry odd, which means that they carry a dipole and they can be excited by light directly. And I will try to use, you know, I will try to discuss experiments in which I use a light pulse which is resonant with the resonant frequency of a phonon, and then I will consider situations in which, although the resonance, the photon energy is low, the field can be very high, which means that one can take say sodium and chlorine, one plus and minus, and I could shake this bond to very large amplitudes. You know, it's not that difficult to get fields of order 10 or more megavolt per centimeter, and if the polarizability to have fields on this strength, and if the polarizability of a medium is large enough, one can easily have, say, 10% distortions. I can think of a material at zero temperature where everything is, you know, is not moving, and then I can choose one single mode and shake it really hard and ask the question, what are the properties of the material if I do this? So before I get into nonlinear phononics, let's go back a second and think and reflect on how we understand linear phononics. So as I mentioned, light couples to infrared active phonons, which means that their coordinate is odd against inversion. And also, those that with bonds that have a significant amount of charge, and this is determined by a particular tensor, which is called the Born effective charge. It's a number that tells you, it's a tensor that tells you how much charge I have in each one of these phonons. And if I think about the excitation of a phonon with light, I can think about basically a damped harmonic oscillator. I have an energy, so a phonon in a laser field can be discussed in terms of the energy of a spring, which is proportional to the square of the generalized coordinate. And then there's a term in the energy that is proportional to, again, the bond charge, which is this quantity, the laser field, and the coordinate itself. So this boils down to a damped harmonic oscillator that is driven by the laser field, and with a prefactor that tells me how polarizable the medium is. The Z star is basically the oscillator strength of this. So once we know this, let's think in the same way that we do in nonlinear optics, what happens if the light field is very large? So this number here becomes very large. And you know, how can we, as we do in nonlinear optics, we can start expanding this energy. So as before, the linear response was an energy that only depended on the normal mode, IR, which is the mode that I'm resonant with, and on the laser. Now, if I can expand the lattice potential, one of the things that I can do is consider all the terms of the mode that is being driven, third, fourth, and fifth order. And then there's going to be couplings between different normal modes. I'm imagining that this system respects inversion in this. So if the system respects inversion, then I won't have any odd modes here. And there will be couplings in which the driven mode will only come into to even powers. Okay? So, and the first, just to make an example of why this is powerful, I am first going to completely ignore the nonlinearity of the driven mode. So I take this mode, I couple light into it, and I shake it to very large amplitude, but I'm imagining that although the amplitude is very large, the mode is fully harmonic. Of course, this is not true, and so the only thing, sorry, I don't want to make you dizzy here, the only thing that I need to worry about is now how this large amplitude mode couples to the other phonon. So this is the lowest order coupling that my driven mode will achieve on other modes that are in linear response are normal to it. And so if I now think of that potential. So now I have the equation of motion of the driven mode, which is, I told you, is harmonic. So it's basically a linear phonon. This is my laser pulse that is resonant, and then the mode decays due to its own lifetime. And now what I told you is that there's a term on the second phonon mode which goes with q square q. So if I write the equation of motion, there will be a second motion of the second phonon, which is coupled to this one, which is not driven by the laser directly, but is driven by the square of the coordinate of the first mode. Okay? So although this mode, which is the directly driven one, has a motion that has zero average, the force on the second mode, which goes with the square of the sine, will have a direction. And so now all of a sudden, I can apply a force to any other mode q2, which is coupled in the correct way to the first mode. And I can, oops, sorry. And so the green mode can be pushed in one direction and go. This is the equivalent of optical rectification in nonlinear optics. For those of you that know a little bit about nonlinear optics, this is observed routinely. I can apply a sine wave to a quadratically a second order nonlinear material and rectify the field. Okay? So this is equivalent also to saying that I have two pendula, one that I'm driving directly, and the second one which is coupled in that way, and as long as I'm shaking one, the other one stays tilted at a finite displacement. The reason why this is very interesting is that now I can think in this term to a situation. This is time now. These are two coordinates. This is my driven mode, which, as I told you, shakes. And then there's going to be a force onto the second mode, which has finite area. So this is a pressure term, but it's a pressure term that doesn't change the volume of the system, because these are optical phonons. And it's a symmetry selective pressure term. There's selection rules that tell me how this mode can couple to that. And so in principle, I can deform the lattice in a surgical way and try to create transient crystal structures. Now, I will not belabor this too much. I want to get to a couple of things that are more interesting. We've worked a lot on this, but there's many things that one can do if I take a structure. For example, this is some oxide structure in which the bonds are tilted. And in principle, by doing the right phononics, I can create transiently the same structure, but I can tilt it straight without changing the volume. For example, in some of these oxides, the properties change enormously if I change an angle a little bit. So these are 4 transition metal oxides, and these are basically all systems in which I only have one d electron close to the Fermi level. So these are seemingly the same, except that because of the structure, there's a bond angle here. Here's the transition metal, and here's the oxygen. This bond angle changes by a few degrees, and the conductivity goes from being a metal to an insulator and changes by many, many orders of magnitude. Okay? So this is an example, and in principle, what I would like to do is just simply go to surgically onto one single bond and move it. Now, the chemists have been trying to do this bond selective chemistry for a long time. This is very hard because in chemistry, you need to take 2 atoms and move them very far apart. In this case, I only need to move things by a very small amount. Sometimes, a 0.1% pressure changes things enormously, and even very subtle changes in the bonds in solids because of the cooperative response of all these atoms. So this is basic. And as I said, I spent years giving people details about this lowest order nonlinear phononics. One example is one in for example, some manganites, in which one can, these are the so-called colossal magnetoresistive manganites, and I won't tell you too much about them, but I can only tell you that in some of these materials, one can go by changing the bond angle by only a few degrees, one can change the conductivity by, say, 7 orders of magnitude. There's hidden phases that one can access, for example, by pressure or by other forms of stimulation. And we showed that by pumping a phonon in a system that has a 2 eV gap, I could create a phase that is not thermally accessible, which becomes a metal. So that's one example. Another example, again, just flashing this here, is recent work by my student who's just graduated now, Tobianova, who has taken strontium titanate, a known failed ferroelectric. Strontium titanate is a system that looks like it's about to go ferroelectric, but it never does. There's many ways to think about this problem, but what Tobia has shown is that if you do the right phononics, you can induce a ferroelectric state in the material and break actually a specific inversion symmetry by light. Okay, so these are some of the examples of things that can be done. Now, and we've been now. The point is that by playing in this way, there's a whole list of things. You can open a book of nonlinear optics and start playing around. And if you know how to build lasers that are resonant with specific phonons, you can do all sorts of things. This is a very beautiful, for example, term that we're exploring. This is squared in both phonons. This can generate squeezed paths of phonons. This is something where you can amplify phonon fluctuations. We've been doing experiments in which you mix two phonons and make the atoms go in circle, basically mimicking what circularly polarized light does. There's lots of things that can be done. But now, in my talk, I'll tell you about this term, and then I'll tell you about something else. Okay, so this is some recent work that, I suppose it's colloquium friendly enough that and it will carry enough information also for non-experts. So what I told you before when I started telling you about the rectification is that I was going to ignore all these terms. So I made the driven phonon completely harmonic. Now I'm going to do the opposite. I'm going to ignore the coupling with my driven mode to other modes, and I'm only going to consider the anharmonicities of my pumped phonon. So what I would like to have is a system. So is a material in which let's say the interatomic potential is highly anharmonic with respect to the motion of some atoms. So we take a ferroelectric. You can take any one of the ones you want. We take lithium niobate because lithium niobate is a material that is highly nonlinear and it lends itself to nonlinear optical studies. And as these ferroelectrics are, what they do is they have two states with different polarizations, and these are acquired by distorting the lattice along the coordinate of one specific mode, which is the well-known soft mode. What we're going to think of is not the soft mode, but another one, an ancillary mode that we drive, and we're going to look at the nonlinear phonon response of this just to demonstrate the point. So basically, this is if you take lithium niobate and you drive QIR to large enough amplitudes, what you're going to get is an energy potential that now depends only on QIR. As I said, I switched off the coupling to all the other modes. This system breaks inversion because it's in the ferroelectric state. So you will have both even and odd expansion terms of my potential. So my energies, as I told you before, is going to be all sorts of terms of expansion plus the contribution that I gave you before from the laser and the coupling. So what I want to do is to drive a mode to very large amplitudes and then have a means to study the response of the system as a function of time. Of course, what I would like to do is to have an X-ray pulse that can be made synchronous not only to the drive. This is my pump pulse, which drives a specific high-frequency phonon of the system. And what I need, I need to do a couple of things. What I would like to have is a pulse in which the absolute phase of the mid-infrared light is in register with its envelope. I want the absolute phase not to change because the way these experiments are done is by doing the experiment many times and repeat and change the delay between multiple pulses and studying the response. What I want to do is to push the phonon to the right or to the left at every pulse always at the same time. So there's a little bit of technique required to do this. And then secondly, I would like to have a probe pulse, for example, an X-ray pulse, which is, however, synchronized with respect to the phase of the first pulse. This is technically not straightforward. I'm going to do the next best thing, which is to use a second visible pulse, which is short enough so that it interrogates the ferroelectric at different times along this pump pulse. Okay? And what I'm going to look at is not the transmission, but the second harmonic generated by the system. So imagine now to have an odd mode. Take a system that respects inversion, that is not a ferroelectric. And now I drive a infrared active mode up and down. What this thing is going to do is going to break inversion up and down at twice the frequency of the phonon, which means that I will get a second harmonic that gets larger and smaller and changes phase following my drive, okay? And for various reasons that I won't belabor, the way this experiment gives you a signal, which is the second harmonic of the probe, which is not proportional to the coordinate of the phonon, but it's proportional to its derivative. It has to do with the fact that I have a time-dependent nonlinear tensor, which then basically gives me the velocity of the phonon. Okay, this is data. So if I pump my ferroelectric with a pump pulse that is weak, the response, so this is now second harmonic intensity as a function of pump probe time delay between the field of the pump and the probe. And if the pump is weak, what I will get is a perfectly harmonic, damped harmonic oscillator, which is the same that I promised at the beginning, was going to be the linear response of a phonon. However, if I drive this to very large, if I drive the phonon to very large amplitudes, I start getting all sorts of anharmonic responses. And this is a spectrum of the red curve that I showed you before, where I don't simply see the driven mode, but I see all its harmonics. So these are highly driven overtones, all coherent with one another. And if you squint and if your eyes are loving enough, you can see a fifth and a sixth harmonic there, okay? And so this is nice, but what makes this, in my view, especially interesting as an application is the following reason. So as I told you, we are measuring a signal as a function of time that is proportional to the velocity of the mode, which means that now, modulo a constant that I don't know, I have a measure of the kinetic energy of my mode, okay? So let's see. I have now, and then what I'm going to do is I'm going to wait until the pulse is gone, because of course here I was pumping the system, I was putting work into the system, and so the phonon was being accelerated. When I stop driving it, then I have an oscillator that is going backwards and forwards. So I can say that the kinetic energy, which I'm measuring down to a constant that I don't know, plus the potential energy, the interatomic potential energy, which I don't know, is equal to a constant. And I decide that this constant, of course the constant will be different at each one of these oscillation periods because the phonon is going to damp. But I'm going to decide that this is a constant at each one of these cycles. So now I can do trivial math and decide that I can measure the interatomic potential as a function of Q at each one of these cycles down to a constant. Okay, so at each one of these cycles, my phonon will be exploring the interatomic potential in this way. So now I'm at far delayed times where I'm only exploring, because the total energy of the phonon is small, I'm only exploring a small excursion. But then now I come earlier in time, and that's good because I'm exploring the same, and then I'm seeing a little more. And then earlier in time, earlier in time. And so what I get is something that is a measure of the interatomic potential. Now, mind you, when people try to measure the interatomic potential of a phonon, they will do a Raman scattering or a neutron scattering measurement. They will look at the line widths. They'll be fitting them very hard to just explore anharmonicities down to here. In this way, I can select one particular mode and explore that coordinate. So now this is lithium niobate is not anything to write home about. So you can take a DFT expert that calculates this, and you can now go back to him and say, look, or to her and say, look, you're doing a good job in the first, second, and third expansion term, but your fifth and sixth is really not that good. And what's quite interesting at some level, at least to write a paper, is that because you can also say that because the interatomic potential is a 3n minus 3 dimensional space, and I have 3n minus 3 phonons, so if I build 3n minus 3 lasers and I do the experiment so many times, I can map the interatomic potential in an interesting way. So for full disclosure, this is the only system in which we've been able to do this, because every time when we looked at strontium titanate, we turned it ferroelectric. So it was great because we wrote a science paper on it, but we haven't been able to study any interesting physics. But at least at some level, this shows some of the power of this phononics. So how am I doing with time? okay, very good. So I'm going to switch gear a little bit and tell you about the physics of nonlinearly driven cuprate superconductors, which is something that really is something that I find highly interesting, and I hope to be able to sort of explore it at the correct way. So in all this list that you can, at every talk you give, you can add a term in the list. What we're very interested in is finding means to use these phonons at some order, or maybe pairs of phonons, and coupled to some specific order parameter, and specifically the superconducting state. So, in what you put on proposals is you show this plot, and you say, well, you have a red electron and a blue electron, and you know that phonons pair them, and so if you drive it the right way, you could stimulate. The great dream of mine is to stimulate the superconducting transition in the same way that one can have laser action or super radiance or things of this nature. Can I create complex orders and by sort of supplying the force for many body interactions from outside? So we've been sort of obsessed by this for a long time, but I will show you some results about this specific material, which is this one of these cuprate superconductors. This is a plot of yttrium barium cuprate. It's a 90 Kelvin superconductor. It's a bilayer compound, and this is one of the many incarnations of the phase diagram of this material. So what one can do is change the doping of holes in the plane of this material, and what one finds, this is one of the great surprises of the late 80s that generated at least one Nobel Prize. Let's see. So what people show, what it becomes clear is that if you put anywhere above, say, between 5% holes and say 25% holes, one finds a superconducting superconductivity at basically room temperature divided by 3. So this is a ceramic which creates an unprecedented scale for superconductivity. There's been a lot of studies, and there's this mysterious phase that I will be discussing, in which some features appear to be those of a superconductor, including some spectra, optical spectra, some electronic spectra. This is why this is called the pseudo-gap phase. It has a gap that kind of looks like the superconducting gap, except that the system is not superconducting. There's many features here that reveal the proximity of this phase to the superconducting state. Another important point that I will not be telling you, there's too much about. There's a lot of discussion of whether this pseudo-gap phase is basically a superconducting state already, in which, however, the correlation length of the superconducting state is not long enough to create a fully formed superconductor. Some people call this a phase-incoherent superconductor. So some people will argue that this pseudo-gap phase is basically a failed room temperature superconductor. And so this is exactly where we would like to be playing around with our phononics to see whether we can teach this system to act properly. Okay, so let's see. Because these phenomena are going to be transient, normally the way you diagnose superconductivity is by looking at the DC properties. So superconductivity is basically a DC phenomenon. So there's maybe saying a transient superconductor is basically not a superconductor. But so one would look at infinite conductivity at zero frequency and perfect diamagnetism at zero frequency, the so-called Meissner effect. However, there's also signatures at finite frequency in the optical spectrum that usually are considered synonymous in equilibrium with the superconducting state. So if I look at the optical response of a superconductor in equilibrium below the superconducting transition temperature at long wavelengths, so this is 1, 2, 3 terahertz, for pulses or for light with the electric field polarized perpendicular to the planes, to the superconducting planes, what one finds are a few key features, especially here I'm plotting the reflectivity as a function of frequency for this material above the transition temperature and below the transition temperature. What one observes below the transition temperature is the appearance of this is basically a plasma edge. It's the same thing that you see in a piece of, say, copper at 2 eV. Actually, copper is not the right example, but is in, say, a metal, you have a plasma edge, at a frequency that depends on the square root of the number of free electrons that I have. In this case, I find a plasma edge, which is related to the density of Cooper pairs that are tunneling between these planes. Okay? And this is an extremely sharp edge at very low frequencies. And this is, other features that I'm looking for is the response in the imaginary part of the conductivity, optical conductivity. So the proportionality constant between the current and an applied electric field tends to diverge toward zero frequency. And in the real part of the optical conductivity, one has basically 0 down to 0 frequency where one has a delta function. So these features are uniquely identified as features of a superconductor. So what we would like to do is to do an experiment in YBCO where we come with a light pulse, we drive the appropriate phonon, in which case we're going to be driving these phonons that move the apical oxygen apical oxygen atoms toward and away from the planes. And I'm going to use a second, so this would be some high frequency excitation. I'm going to use a second TeraHertz probe pulse to interrogate the properties of the system at the frequencies where I'm expecting these superconducting features to appear. And then I'm going to cross my fingers and hope to see transient superconductivity above TC as long as this phone is being driven. Okay? So there is no specific insight, no nonlinear phononics being thought about, except just we did this experiment because we thought something was going to happen. Okay, so once again, we start from the black and we're looking for the red at temperatures above the thermodynamic transition temperature in presence of a shaking of the apical oxygen mode. So what we found was at least at the beginning, what we found, so I am plotting now the changes in conductivity. So I'm taking now the black state, which is the non-superconducting state, and I'm going to show specifically changes in conductivity because the way we did the experiments at the beginning was we had to rely on sort of differential measurements. And what we found was at least something that was convincing enough for us, where we showed that, for example, the imaginary part of the changes in the imaginary part of the conductivity were indicative of a 1/omega-ish response. And for comparison, this curve gives you the change between high temperature and low temperature at equilibrium. So we could generate a change in sigma 2 that was suggestive of a superconducting state, or of the same feature properties of a superconducting state, but maybe about half or 2/3 as big as what one observes at equilibrium. And then again, a plasma edge, more or less in the same position where one finds the same plasma edge by cooling the material. What was striking is that one could observe this up to this is the loss function I wanted. This is basically the inverse of the real part of the dielectric constant. This tells you that basically the dielectric constant is crossing 0 at that frequency, so the inverse has a peak. So what was striking was that one could find this light-induced effect through up to extremely high temperatures. And in fact, as a function of doping, up to the temperature, the edge of the pseudogap phase, this mysterious phase that looks almost superconducting but is not superconducting, could be changed in a way that was suggestive of fluctuations, of superconducting fluctuations. So we've now, since then, and I don't have time to explain this too much, since then validated this data, and you don't need really loving eyes as we had at the beginning to believe in this. Now there's at least the spectra do look like the same as the ones that are observed at equilibrium. Okay, but the problem that I want to discuss with you here, because in the context of this nonlinear coupling between phonons and electronic orders, is one where I try to understand exactly what is this apical oxygen phonon doing, and how is it that by shaking this apical oxygen mode to large amplitudes, I'm coupling to these supercurrent tunneling modes between the planes. So I'm going to discuss the data below TC and then above TC. So basically, this is, okay, one word. Cuprates are, host superconductivity within the planes, and then these planes are coupled by the Josephson effect, basically. So one has different tunneling modes, and normally one has only one frequency, but because these are bilayers, one really has two tunneling modes. One has a tunneling mode between the bilayers and within the bilayers. This is a low frequency mode, and that's a high frequency mode. So the question is, and how is it that this phonon couples to this? So these phonon modes are usually orthogonal to the superconducting tunneling modes. And so the way one can think about this, so this is done very closely with our colleagues at Harvard in the group of Eugene Demler, who's been helping us to understand the basics of these couplings. And what they told us is that, look, if you take these apical oxygen mode and you drive it to large enough amplitudes, these are the energies, the contributions to the energy, the linear energy of the three normal modes. The lowest order coupling is going to be one which is proportional to the amplitude of this odd phonon, and then the product of this specific tunneling and that specific tunneling. I could walk you through the math, but I would put you to sleep and lose 3/4 of the audience. So you're just going to have to believe me. Whereas Q, this is a momentum in the planes. Okay? So there's higher order terms, but this appears to be the strongest coupling term. Now, this may seem a little weird, but if you write the equations of motion, this is what you're left with. This is the equation of motion of the phonon that I am driving. Now, these are the equations of motion of the two tunneling modes that I showed you above. These guys, J1 and J2. And now what I have is basically the equation of a three-wave mixing process, which basically, this is, those of you that build lasers, I don't know how many of you build lasers, they know about optical parametric amplification. One mixes three waves and uses one high frequency wave to amplify two low frequency waves at a frequency which matches, in which some frequencies are matched. So what this three-wave mixing process tells you is that pumping this phonon parametrically drives oscillations in these plasma modes at finite momentum. The important thing is that because of symmetry, this does not happen at k = 0, but it only happens at finite momentum. Basically, the way one has to think about this is that this phonon generates pairs of these Josephson plasmons, and it selects a pair of momenta, plus k and minus k, so that the frequency is respected. Okay? And there's very specific predictions. This is now a calculation solving these three equations of motion of the current perpendicular to the planes as a function of time, where this is my driven mode, which decays into two plasma modes. This is the high frequency J2, and this is the low frequency J1. Okay? This is, again, very simple, classical three-wave mixing that one expects. Okay, so my student, so normally, if you want to measure the coherent responses in a material, people do a pump and then use a probe pulse, say in the visible. They look at the reflection, and then they measure the reflection onto. This is the basics of a pump probe experiment. However, this experiment really only measures totally symmetric modes, whereas, again, if I pump here and I look at the second harmonic of the probe, I'm going to measure the odd modes. This is basically the same experiment that we did for the ferroelectric. So the bottom line is that by measuring the second harmonic as a function of time, I can measure all the odd modes, but also the supercurrents. As these supercurrents go backwards and forwards coherently, they will break inversion, and they will putatively become measurable if the modulation of the nonlinear optical nonlinearity of the second order nonlinearity is large enough. So Alex set out to do these measurements, and sure enough, you can see in the pump probe experiment, you pump the phonon, and then you look at these ringing. So this is basically the same experiment that we did before by measuring the TeraHertz reflection, but now we're measuring the coherencies in the second harmonic as a function of time. So now let's first check whether what these guys say is real. So we go below TC, where there's preformed superconductivity. We know that there are these superconducting plasmons, J1 and J2. We know what the phonon is, and we just want to know whether we are really generating coherent supercurrents driven in this way. So sure enough, what Alex showed is that this is data. You pump the phonon at low intensities, say 0.5 megavolt per centimeter. This is my pumped phonon, which then rings for a while. But if you look at here and you Fourier transform this, you will find that these are two pumped modes for reasons that I won't tell you. This thing decays into two modes which are somewhat at the sum frequency of which matches the yellow. And when you go to larger amplitudes, these two guys decay into this and into a huge peak at low energies. Okay? And so basically what I have is that pumping a phonon here generates this interlayer tunneling currents that oscillate backwards and forwards in the superconducting state. And so what I know is that A, the frequency, the prediction of the sum frequency matching is correct, and also because I know the dispersion of these modes, or at least I can calculate it. This is a solution of the equations of motion. I can see that my plasma mode is being generated at a frequency which is commensurate with the generation at that momentum. So, and again, the second prediction was that this is a parametric process, which means that I am taking fluctuations of the superconducting order in the superconducting state and I'm amplifying them. Okay? So now what I can do is now, because I can measure this phonon and this, I can plot this as a function of this. These are two measured quantities. And so what I find is over 3 orders of magnitude, this Josephson current is being amplified exponentially, as I was expecting for a parametric process of this nature. And this is great. And the theory really can be used to fit the data. Sorry, no, that's not true. The fitting function that I take from the data can be used to fit the theory, calculated at different phonon amplitudes. And so basically, okay, this is too much information. Is there a reason why I am being told that there's no more? So I don't think this is working as well as it could be. We might not get to the end of this talk. Oh, done. Fantastic. Thanks. I probably kicked it. Okay. So now, one more important point. Because my three-wave mixing process, amplification of the superconducting order parameter is happening, I would expect this effect to go away at TC, because I know that this is an equilibrium spectrum. This is the loss function where I see all the zero crossings. I know that this specific Josephson plasmon in equilibrium goes away at TC exactly. At k equals 0, which is where I'm measuring, the Josephson plasma fluctuations with correlation lengths of 300 microns at 1 terahertz disappear exactly at TC. So, and this is very different from all the other phonons, which really continue all the way. So in principle, if I redo the experiment in the normal state, my three-wave mixing signal should go away. Okay? So surprise, surprise, what happens is that by pumping these two phonons, this was the experiment I showed you before, it was at 5 Kelvin. When I go to 100, 200, and even at 300 Kelvin, I still see this Josephson plasma peak at finite momentum driven by my pump. Okay? So one important point that I don't think came across very clearly. This equilibrium peak is measured in equilibrium at k equals 0. My putative amplified fluctuations are measured at finite momentum. So these are two slightly different things. Okay. So this is what I showed you before. This is, again, the amplified Josephson plasmon. And this is at room temperature. I still see an amplification of a mode that is smaller, but it's still there. Okay? And now in this specific compound, I can see that this amplified mode goes away exactly at T star, which is the edge of what I told you before this mysterious pseudo-gap phase. So what I did is that I can measure in a different compound, redo the whole experiments, meaning Alex can do this. Another sort of 8 months of his life. And what you can see is that if you take a different compound, it doesn't go away at 380 Kelvin, but at higher dopings, it goes away at 270 Kelvin, okay, in YBCO 6.65. Unfortunately, if you go to higher dopings, in case you were going to ask this, the frequency matching between the phonon and the two plasmons goes away. So this is not a comprehensively applicable method. It's just something where we are getting lucky in this specific compound and we're able to see this, okay? But this matches very well. This is stuff that I stole from various publications, and I can generate these parametrically amplified oscillations, which I'm attributing to the Judson plasmon, all the way to room temperature. Okay, why didn't people see this before? So there's been 100 people have measured these plasmons as a function of temperature, but the way they measure this is using linear optics. So in linear optics, you're only sensitive to pairs of frequency and momenta, which are within this cone, the so-called light cone. So there's lots of, I think Tom Timmusk at McMaster was the first person that saw this. Many people. What we're showing here is that there's fluctuations that we're amplifying outside the light cone, okay? And so this is an area, a position for these plasma fluctuations that has been inaccessible until now, because basically all other inelastic scattering probes don't have enough resolution to go to 1 terahertz, and the linear optics doesn't get to these moments. So these are basically, say, 2 terahertz fluctuations with 5 microns correlation length. And so this cannot be seen by linear optics. So at least this is the way we're interpreting this. It's nice, and now there's new calculations that seem to indicate that if this is true, then, and if I shine a linear terahertz light pulse at these frequencies, I will get plasma edges and amplification. This has got to do with basically solving Maxwell's equations in the correct situation. So maybe that's what I should say, that the conclusion of this last part of the work is that, firstly, TeraHertz 3-way mixing seems to reveal and amplify superconducting fluctuations in the normal state of cuprates, which were to date invisible. And secondly, what I've been annoying lots of people by calling this process light-induced superconductivity, which is, of course, light-induced room temperature superconductivity, which is, as you can imagine, a highly, bold statement. But what I'm becoming convinced of is that this light-induced superconductivity is some form of manipulation and amplification of pre-existing superconducting fluctuations in all materials that should be understood as phase-incoherent superconductors above the thermodynamic transition temperature. There's basically paraplasmons at finite momentum that don't quite have sort of established correlation lengths that are large enough to give me superconductivity, which I can try to. And this actually has a lot of, well, firstly, I don't have time now, but those of you that are interested in hearing more, we've validated these observations in other materials, some organic materials, which are also known to be phase-incoherent superconductors, or at least have signatures in some transport measurements of phase-incoherent superconductivity. And there seems to be some correlation between this statement and reality. The second thing that I would like to say is that if this is true, there's a lot of very interesting physics that we can, or techniques that we can copy from the physics, for example, of exciton-polariton condensation. There's many, we can put this in cavities. We can start shaping this, and with the goal of stabilizing this state in some way and be very happy and be able to make a room temperature superconductor in CW. Maybe if we could just increase the coupling strength of our light by a couple of orders of magnitude without dissipating and heating everything up to 1,000 Kelvin and melting everything, maybe we can do it. So what am I going to say? It doesn't hurt to, what do they say? Dreaming is free. So, but more generally, I sort of gave you a snippet of the things we do, which are about the use of phononics and to manipulate materials, to steer them with light. These are all sorts of pictures which belong to a different talk where I discussed dynamical stabilization of various phenomena. This is the dream of generating a pulsed room temperature superconductor, etc. I should really finish this by thanking the people that have done this. So let's see. Most important people are Alex von Huggen, who did all these experiments in second harmonic, both in the ferroelectric and in this cuprate. Biao-Long Liu is a guy that built sources that now make it possible for us to pump any phonon we want. We can generate terahertz pulses with, say, 3% bandwidth and pulse energies of many microjoules. So we can create electric fields of, say, 10 megavolt per centimeter anywhere we want in the spectrum. So this is really an incredible achievement of this student of mine. Tobia Nova is my student that I'm just because he's been helping a lot and he's been doing this ferroelectric experiment. Michael First is a senior scientist. One of the great things in Max Planck is that you can have staff scientists that know a lot more than you in everything, and they can sort of run things. Daniele Nicoletti is also another staff scientist who teaches me optics. Roberto Merlin is a friend from a long time from the University of Michigan who teaches me Raman scattering, and I don't even have to pay him. And Michael Fechner is a theorist in my department that helps us understand just basic DFT and which phonons couple to what and elementary ideas. So I thank you for your attention. I hope I didn't talk too much. It's already 1:30 here, so it's yeah.